Welcome back everyone. Welcome back to this particular lecture called rectifiers. So what is a rectifier? Rectifier is the application of your PN junction diode. Rectification is a process that converts the alternating signal or AC to the one directional signal or DC. Okay, that means it converts the AC signal to not fully DC but pulsating DC. So in that rectifier output we will get the pulsating DC. That means some AC components will still be present in that output signal. So we can eliminate them either by using filter and voltage regulators. Okay. Now we will see how these rectifiers are classified into two types. One is halfway rectifier, another one is a full way rectifier. So this is my circuit of the halfway rectifier. So here what you are observing, we are applying the AC input signal to the primary of the transformer, and this transformer can either be step up or step down transformer, and here we have a diode and a resistor or load resistor RL is connected at the output, and this is my input signal, a sinusoidal input signal. This input signal only I am applying at the input side. Okay, so at the secondary of the transformer, either it can be step up or step down transformer. Okay, now in the secondary of the transformer this signal is appearing. Okay, now during the positive half cycle of the input signal, that means for this part only, what will happen to the secondary of the transformer side? This is positive, this is negative. We are just identifying the polarity of the input signal at the secondary. So for the positive half cycle of the input signal, this is positive, this is negative. Okay, so the positive of the diode is connected to the positive of the input signal, so it will make diode on. Diode on means if it is an ideal diode, the voltage drop across the diode will be 0 volt, so it will be short circuited. But if it is a silicon diode, the voltage drop across it will be 0.7 volt, so I can simply replace by a line. Now this is the load resistance. Okay, so in that case, what is my, if I apply the KVL, I can easily calculate the current I that is flowing through this entire loop. If the maximum value of this input signal Vi is Vm, so what can I write? I equals to Vm divided by Rf plus RL. Why Rf? Rf is the forward resistance. This diode also has some resistance, internal resistance. So this Rf plus RL. Okay. Now if I apply the, during the negative half cycle of the input signal, what will happen? This is negative, now this is positive. So negative of the input signal is connected to the positive of the diode. So diode will be open circuit. So during the negative half cycle of the input signal, my output voltage will be 0. We are just trying to calculate the or observe the output current. Okay, so for 0 to pi interval, during the positive half cycle of this input signal only we are getting the output, but for the negative half cycle of the input signal, since this diode is off, we are not getting any output. So same will repeat. So for all the positive half cycles of the input signal for this particular circuit, we will get the output, but for negative half cycle we won't get any output. Okay, so if I consider that for the input signal we have applied this Vi, right? So if Vi equals to, if we consider Vm sin omega t, where Vm is the peak value of this signal, so what is the current flowing through the circuit? Current will be Im sin omega t, that is Vm by R, right? Vm by R or Vm by Rf plus RL. So only 0 to pi interval, only this interval I am getting the current, but for pi to 2 pi interval I am not getting any current, that is why it is 0. Okay, now Let's proceed towards the full wave rectifier. So full wave rectifiers are classified into two types. One is center tap full wave rectifier, another one is a bridge rectifier. So how this full wave rectifier circuit operates, let's see. So in the full wave rectifier also, primary side we are giving the AC input signal. So this is my secondary side. Okay. So in this center tap full wave rectifier circuit, you can see that in the secondary side, the center of the secondary side, it is tapped. That means if there are total 100 turns in the secondary side, 50 turns will be in the upper half of the transformer secondary and 50 turns will be at bottom half of the transformer secondary. Okay, that means the voltage induced at each half, at the top half and the bottom half of the transformer secondary, will be equal in magnitude but opposite in phase. Okay, now here you can see we have connected at the center of the transformer secondary, we have connected a load resistance. Now we need to calculate the current, what is the current flowing through this load resistance. And here in the top half of the transformer secondary, we have a diode D1 connected, and at the bottom half of the transformer secondary, we have the diode D2 connected. Okay, now during the positive half cycle of the input signal, what will happen? This is positive, this is negative, this is positive, this is negative. Positive half cycle of the input signal means when the input signal polarity is, this is positive, this is negative. So this is positive, this is negative, this is positive, this is negative. Input signal we have applied is Vi. So when this is positive, what will happen? This diode D1 will be on, positive positive connected, so it will be on, means short circuit. So what is the current flowing through this D1? Let's say it is I1. So at that so in this case I1 current is flowing through this RL. But what will happen to this diode D2 now? You can see positive side of the diode D2 is connected to the negative of the input supply. So this diode D2 will be off. So no current will be flowing due to this D2. Okay. Now coming to the negative half cycle of this input signal. Here it is negative, now here it is positive. So similar way the polarities will be changed. Now here it is negative, here it is positive. Again here it is negative, here it is positive, when we are considering the negative half cycle of the input signal. So if it is negative, now what will happen? This negative and positive of the diode D1 is connected, so D1 will be off, means open circuit. So no current will be flowing through this load resistance RL due to this D1 now. But now this is negative and this is positive. For the bottom half of the transformer secondary, this positive is connected to the positive of the diode D2. So D2 will be on now and the current will be flowing through this diode D2. Let's say it is I2 and the same current is flowing through the load resistance RL. So we can see for both the half cycles of the input signal, the current is flowing through this RL. For the positive half cycle of the input signal, this diode D1 is on, so current I1 is flowing through the RL. For negative half cycle of the input signal, this diode D2 is on, so I2 is flowing through the RL. So what is the total current I flowing through this RL for both the half cycles of the input signal? I1 plus I2. Now if we plot this situation in the waveform, this is my AC input voltage that I am applying to the primary of the transformer secondary. Now we are measuring the output in terms of current that is flowing through the load resistance RL. So this I1 current I am getting during the positive half cycle of the input signal when this D1 diode is conducting. Okay. Now when this for the negative half cycle of the input signal, what is happening? D1 is off, D2 is on. So this I2 current I am getting when D2 is on for the negative half cycle of the input signal. So if we sum this I1 plus I2, we will get these full cycles. Okay. That means for both the half cycles of the input signal, I will get the output. Now there is another type of full wave rectifier which is called the bridge rectifier. So here also we are applying the AC input signal at the primary of the transformer, Now this is the secondary of the transformer, and in the secondary of the transformer we can see that four diodes, they are connected in the fashion of Wheatstone bridge, and here we have the load resistance RL. Now we have to calculate what is the current flowing through this load resistance RL. Okay, so for the positive half cycle of the input signal, this is positive, this is negative. So similarly, in this secondary of the transformer, we will get this is positive and this is negative. It can be a step up or step down transformer. So it will just modify your magnitude of the voltage, nothing else, right? But the polarity of the voltage will remain same. If my input signal for the positive half cycle of the input signal, this is positive, this is negative, means uh, here also it will be positive, it is negative. So when it is positive, we have to check which among these four diodes are conducting. Here it is positive, means D1 is on and D3 is on, while D4 and D2 are off. Okay, so in this case the current, let's say I1 is flowing through this RL resistor because of these two D1 and D3 diodes. So come for the next half cycle of the input signal, this is negative, this is positive, so this will be negative, this will be positive. That means here it is negative. If it is negative, that means which diodes will be on? Obviously negative positive, that means diode will be off, right? So in this case D4 and D2 will be on only, and the current that is flowing through this load resistance RL will be due to this D2 and D4. Let's say this is I2. So we can see that for both the half cycles of the input signal, the current is flowing through the load resistance RL, and the waveform will look similar to this waveform. Okay. Now, if we want to calculate the RMS value and the average value of the half-wave rectified sine wave, so we have already seen how to calculate the RMS and average value for a periodic signal. So this is a case study. See, for half wave rectified sine wave, this is my output value of the current. Okay, now we have seen that only for the 0 to pi interval for half wave rectifier, what was the output? 0 to pi interval only, we have this value. For the negative half cycle, the diode is off, so we don't have any value. Okay, so what was the formula to calculate the RMS value? This first we are calculating the mean square value, then to get the RMS value we just can take the square root. So in order to calculate mean square, what was the formula? 1 by capital T. Capital T is the total time period. So total time period is, what is time period of a signal? We have studied. It is the time that takes to complete one full cycle. Okay, so these, for this signal 2 pi is the time period. That is why the formula is 1 by capital T, that means the time period, then integration of 0 to 2 pi this I dt. So 0 to 2 pi, how will we write? 0 to pi, we have the value of the current Im sin theta. Okay, what was the formula? 1 by capital T integration of 0 to t xt square dt, right? So that is why it is I square m sin square theta. Okay, but pi to 2 pi, what is happening? We don't have any value of current because the diode is off, so it will be 0. So if you integrate and put the limit, we will arrive here Im square by 4. So this is, we are calculating the mean square value. So in order to get the root mean square value, we have to take the square root of this value. So we will get Im by 2. Similarly, how to calculate the average value? What was the formula? 1 by capital T integration of 0 to capital T xt dt. So what is my capital T? This is 2 pi, full time period, 2 pi, integration of 0 to capital T is 2 pi, then Im sin theta d theta. So this 0 to 2 pi, we can break 0 to pi and pi to 2 pi, but we have this current value for 0 to pi only, pi to 2 pi it is 0. So if you calculate, you will get the average value for half-wave rectifier as Im by pi. Now come to the RMS and average value for the full wave rectifier. Okay, so for full wave rectifier, we will consider the time period. First we will calculate the mean square value. No, what is the formula? 1 by capital T integration of 0 to capital T x square t dt. But here for the full wave rectifier, previously half wave rectifier we were considering the time period as 2 pi, right? But for full wave rectifier we will consider the time period as pi, that means t by 2. Why? Because you can see this full wave rectifier is repeating its um, value, repeating the waveform after t by 2 time period. Okay, because for the negative half cycle also it is negative half cycle of the input signal, this full wave rectifier is giving my positive half cycle. So after t by 2, this till this 2 pi is my capital T complete time period, this pi is my capital T by 2 half of the time period. So after t by 2 it is repeating the waveform. That is why for full wave rectifier the time period capital T we will consider as pi instead of 2 pi. So rest of the things will remain same. 0 to pi, what was the value of this im sin theta? So we will take I square m sin square theta d theta, since we are calculating the mean square value. Now if I want to calculate the root mean square value, we have to take the square root of this mean square value. Similarly, to calculate the average value, the period will be taking is 1 by t by 2, half of the total time period. Total time period is 2 pi, so we will take pi only, because after pi you can see this full wave rectifier, it is repeating its waveform. So it will be 1 by pi integration of 0 to pi im sin theta d theta. After integrating and putting the limits, we will get this value as average value, that is 2 im by pi for full wave rectifier circuit.